the different kinds that we'll see is like, let's say, a spring. And it could be a horizontal motion like that, or it could be like a spring like this hanging, and then you can pull it, letting go of it, and it can go up and down. So we want to see this, the physics of that. Or let's say a string with some small ball hanging at the end of it. You can let it go, and it goes back and forth. This is known as a simple harmonic motion. And this is known as a spring oscillation. Spring oscillations. And this one, you can have a ruler or any other kind of extended object. You can let go of it and you can go back and forth. That's known as a physical pendulum. So the difference between physical pendulum and simple harmonic, actually, sorry, this one I should have, this one, the name is simple pendulum. The simple harmonic motion is the whole, everything put together, but simple pendulum is this one, physical pendulum is that one. The only difference between these is that this one, the simple pendulum, can be considered as if it's a little point object. So the dimension of the object itself is negligible, and the only thing that matters is its distance from the pivot point, L. So it's supposed to be, most of the mass is supposed to be concentrated at that point, and then it goes back and forth. So that's what the simple pendulum is. It's just like a tiny object where its size can be ignored, and you release it, and then you let go of it. It goes back and forth. The physical pendulum is an actual object where its mass is distributed throughout its length. So it could even be any other object, like it could be a sphere that has a little hook on it, like this, and you can let it go, and it goes back and forth. You know, it goes back and forth. So it doesn't have to be a ruler or anything. It could be any physical object where it's rotating about some point. And then there's the torsional pendulum. So these two are both physical pendulum. And then there's the torsional pendulum. And the torsional pendulum is something like you have a string, and then you have some kind of object hanging from that string. It could be a disc, or it could be a sphere. And the idea of the torsional pendulum is that you rotate it, and then you let go of it, and it goes back and forth like this. Like that. Okay? So it goes back, and forth, and then same thing here. So one of the basic questions that we would like to ask about all of these four kinds of motion, torsional, physical, simple, and spring, we would like to know what is the frequency and period of the motion. What's the formula for that? Okay? In today's lecture, I'm going to focus not so much on the derivation of how we get it, but I'm going to focus more on, I'm going to show you what the formula is, and then I'm going to focus on how to use it, you know, because that's more important for our purposes. So you could actually look at my notes as well. I have notes online where I go through the derivation of the formula, where I actually show how to get it. But right now I'm going to focus on using it. So it turns out that the frequency of this is equal to omega is square root of k over m. So omega is known as the radial frequency. It's measured in rads per second. Okay, and the actual frequency is equal to omega divided by 2 pi. And that's measured in cycles per second. The reason why is because if you have omega is in rads per second, 2 pi rads is equal to 1 cycle, right? So if you divide a radian by 2 pi, you get 2 pi rads is in 1 cycle, so it becomes cycles per second, which is known as a hertz. Okay, so omega divided by 2 pi is equal to F. F is known as cycles per second or revolutions per second. So that's the one that is usually, this is what we usually mean when we say frequency. It's measured in hertz, Z for abbreviation. So the frequency of this is 1 over 2 pi square root of k over m. Okay, and the omega square root of k over s. So if you remember what the omega is, just divide it by 2 pi and you get the f. And then if you invert the f, you get seconds per cycle, which is usually just you eliminate the cycle and you just write it as seconds. What that's telling you is how many seconds does it take for the cycle to repeat every cycle. How many seconds does it take? This is known as the period of the motion, t. So t is 1 over f, which is seconds per cycle, which is usually just written as seconds. So the period of the motion will be the inverse of this, 2 pi square root of m over k. Okay. Now, at this point, let me mention a couple things. Remember way at the beginning of the semester, actually the first day, I told you about units. I told you whenever you have a formula or a definition, the units have to work out. Okay? So if I this one actually is a formula. It's an actual derivable formula. So if I'm telling you the formula for period is 2 pi m over k, I should be able to show you that the units work out. So let's actually go through this, see if it does work out. If you have square root of kilogram over, what's the units of the spring constant k? The spring constant k, it's in units of what? Remember Hooke's law, F equals kx. Negative kx. So this is in newtons, this is in meters. So the spring constant has units of newtons per meter. Okay? So if this is a kilogram, the spring constant has units of newtons per meter, the units should work out. Okay? So the meter goes up to the numerator. And then Newton is force, which is mass times acceleration, right? So kilogram times meter per second squared, right? So the kilogram cancels the kilogram, meter cancels the meter. The second squared goes up to the numerator. Which is a second. So as far as units, the formula is working out. Mass over k, square root, works out to be seconds. So does that prove the formula? Not necessarily, because it doesn't prove the 2 pi. Right? It doesn't prove that there should not be anything else here, like 3 or 4 or 5. It doesn't firmly prove the formula, but it shows that at least it has the right units. You know.